To capture the oldest light in the universe, you have to look for faint infrared energy traveling across billions of light years of expanding space. The Hubble Space Telescope was built primarily to observe the visible spectrum. Its sensors were not designed to detect the subtle, stretched wavelengths of ancient infrared light. There is a severe physical catch to observing infrared light. Infrared is essentially heat radiation. If a telescope has any warmth of its own, the infrared energy radiating from its own instruments will blind its sensors to the distant galaxies it is trying to observe. The entire observatory must be kept freezing. This map shows the James Webb Space Telescope's location at the Second Lagrange Point, or L2. Positioned 1.5 million kilometers away from Earth, it sits in a gravitational balance point far removed from the direct radiating heat of our planet and the Moon. Surviving in this extreme isolation and capturing a single usable image demands a sequential pipeline of thermal protection, intense light gathering, and deep space communication. Before the telescope can process a single photon, it has to actively defend itself from the sun. The defense mechanism is a sunshield roughly the size of a tennis court. It consists of 5 distinct layers of a heat-resistant material called capton, each coated in aluminum and doped silicon to maximize reflectivity. This diagram illustrates the shield's thermal mechanics. The 5 layers never touch. Instead, they act as a V-groove radiator. When solar radiation hits the first layer, the trapped heat deflects and channels horizontally, escaping into the vacuum of space before penetrating the next layer. By the 5th layer, the temperature plummets to 40 Kelvin, or minus 390 degrees Fahrenheit. This massive thermal drop provides the perfectly cold, quiet canvas required for the telescope's sensors to detect the faint heat signatures of distant stellar formations. To collect enough light, the telescope required a primary mirror 6.6 meters across. A solid piece of glass that size could not physically fit inside the payload fairing of the Ariane 5 launch vehicle. Engineers solved this by building a segmented mirror. The surface is divided into 18 separate hexagonal pieces that could be folded up for launch and deployed in orbit. Each segment is forged from beryllium, a metal chosen because it remains incredibly rigid and holds its shape in extreme cold. The surface is then coated with a microscopic layer of gold to maximize the reflection of infrared light. This animation shows the alignment process. Behind each segment are mechanical actuators capable of shifting the metal along 6 axes. Using a wavefront phase technique, operators incrementally adjust the segments until their individual reflections merge, forming a single, precise optical surface. Unfolding and aligning a 6.6-meter mirror in a frozen vacuum provides the immense light-gathering capability needed to see further and clearer than prior observatories. Once focused, the gathered light hits the Integrated Science Instrument Module, where it is converted into digital data and temporarily saved to an onboard solid-state recorder. The next hurdle is logistical. The telescope has to physically move these massive, high-resolution files across 1.5 million kilometers of empty space back to Earth. NASA handles this through the Deep Space Network. By utilizing massive radio antenna arrays in California, Australia, and Spain, the network maintains a continuous line of sight with the telescope, regardless of how the Earth is rotating. This chart compares the 2 primary communication frequencies. A lower bandwidth S-band handles essential engineering telemetry and commands. When downlinking heavy science files, the telescope switches to the highly efficient K-band, moving the bulk of data in hours. Without this global radio relay operating around the clock, the data captured by the telescope would remain permanently trapped on a hard drive floating in space. After its 1.5 million kilometer transit, the downlink arrives at the Mission Operations Center in Baltimore, Maryland. On the ground, the raw digital information is immediately ingested into local servers, where it goes through a pipeline of processing and calibration to make it ready for scientific analysis. The finished files are then uploaded to the Barbara A. Mikulski Archive for Space Telescopes, creating a permanent, publicly accessible repository. It is the final step in a process that takes scattered ancient infrared photons and translates them into a cohesive digital file. Through an orchestration of extreme engineering, cryogenic heat shields, and global radio networks, light that has traveled through the void for billions of years finally comes to rest. It sits on a hard drive, ready to provide a clearer look at the mechanics of our cosmos.